At first glance, the skin of a pond appears calm, almost passive, a reflective membrane separating air from water. But for a water strider, this surface is neither gentle nor forgiving. It is a loaded battlefield of invisible forces where physics becomes both architecture and threat. The water strider lives entirely atop a medium that was never meant to be stood upon, relying not on solidity but on tension, a molecular resistance created by water molecules clinging to one another with relentless cohesion. Where most insects encounter water as a trap that pulls them under and drowns them within seconds, the water strider treats it as a floor, a highway, and an early warning system all at once. Its survival depends on reading this surface not as liquid, but as a constantly shifting map of forces. The strider's legs are the first key to this illusion of solidity. Each limb is elongated far beyond what its body mass would seem to require, distributing weight across a wide area to avoid breaking the surface film. The legs are coated in microscopic hairs, thousands per square millimeter, each angled and waxy, creating a super hydrophobic surface that repels water on contact. Instead of piercing the surface tension, the legs dimple it, pressing downward just enough to create shallow depressions without rupture. From above, the insect appears to skate effortlessly, but from below, the water's surface is visibly warped, bent into delicate bowls beneath each foot. This balance is not static. Every movement requires constant recalibration, as even a slight misstep could puncture the membrane and send the insect spiraling into a medium that would quickly overwhelm it. Movement across this weaponized surface is achieved through controlled strokes that exploit the water's elasticity. Rather than walking, the water strider rows. Its middle legs sweep backward in synchronized arcs, pushing against the surface tension itself, generating thrust without submersion. This rowing motion is efficient and remarkably fast, allowing the insect to accelerate, turn, and stop with precision that rivals terrestrial runners many times its size. The rear legs act as stabilizers, adjusting posture and preventing rotational drift, while the front legs remain free for sensing and prey capture. The entire system functions as a living hovercraft, tuned to the narrow boundary between flotation and failure. But the surface is not just a floor, it is a sensory field. For a water strider, ripples are information, and stillness is suspicious. The insect's nervous system is tuned to detect minute vibrations traveling across the water, distortions caused by struggling prey, approaching predators, or environmental disturbances far beyond the reach of vision. When a mosquito larva breaks the surface to breathe, the resulting wavelets radiate outward in precise geometric patterns. The water strider reads these distortions instantly, determining distance, direction, and size of the source. Its response is immediate, a sudden pivot, a rapid glide, and the predator is upon its prey before the ripple has fully dissipated. This ripple detection functions like a biological radar system, but unlike technological equivalents, it operates in a chaotic, analog environment. Each wave interacts with countless others, reflecting off reeds, rocks, and shorelines, creating interference patterns that could overwhelm a less specialized animal. Yet the water strider's sensory hairs and mechanoreceptors are finely tuned to filter this noise. It prioritizes sudden, asymmetric disturbances over rhythmic background motion, allowing it to ignore wind-driven ripples while locking onto the irregular struggles of living organisms. In this way, the surface of the water becomes a constantly updating map of threats and opportunities, one that the insect interprets instinctively without conscious processing. Predators also announce themselves through this same medium. Fish rising from below create expanding pressure waves that betray their approach seconds before they breach the surface. Amphibians displace water in heavier, slower pulses, signaling danger even when hidden by vegetation. When these signatures are detected, the water strider does not freeze or flee blindly. Instead, it calculates an escape vector, accelerating away from the source along a trajectory that minimizes further disturbance, reducing the chance of pursuit. Survival here is not about strength or armor, but about reading physics faster than death can arrive. Storms transform this carefully readable world into something far more dangerous. Rainfall fractures the surface into a chaos of overlapping impacts, each droplet punching through the tension with explosive force. To most insects, such conditions are catastrophic. The surface becomes a minefield of collapsing membranes and violent vibrations, leaving no stable foothold. Yet water striders remain active even during heavy rain, skimming between impacts with astonishing control. Their bodies are light enough that individual raindrops, though massive by comparison, do not immediately crush them. Instead, the insect braces, lowering its center of mass and spreading its legs wider, increasing surface contact to maintain stability. During storms, the ripple map becomes almost unreadable, a constant roar of overlapping signals that would normally obscure prey and predator alike. The water strider adapts by shifting its priorities. Rather than hunting, it focuses on maintaining position and orientation, using visual landmarks along the shoreline and subtle differences in wave direction to avoid being swept into open water or forced beneath the surface. Its ability to stay upright in these conditions is not accidental. Evolution has selected for body shapes and leg arrangements that minimize rotational torque when struck by sudden forces. Even when knocked briefly airborne by a large drop, the insect can recover upon landing, re-establishing contact with the surface film before sinking occurs. Heavy rain also oxygenates the surface layer, altering the behavior of aquatic organisms below. Prey may retreat, predators may become more active, and the water strider must interpret these changes through indirect cues alone. It cannot see beneath the surface, but it can feel shifts in tension, subtle changes in viscosity caused by temperature and dissolved gases. These cues inform its decision to remain, retreat, or relocate entirely. In this way, the insect is not merely surviving the storm, but navigating a dynamic system that reshapes itself with every environmental shift. Despite its mastery of this boundary world, the water strider remains acutely vulnerable to one mistake. If its surface film is contaminated by oils or pollutants, the hydrophobic hairs lose effectiveness, and the illusion of solidity collapses. The insect sinks, legs breaking through the surface tension that once held it aloft. Escape from beneath the surface is possible but costly. The strider must beat its legs rapidly to generate lift, expelling trapped air bubbles and fighting against adhesion that tries to pin it below. Many do not succeed. This sensitivity makes water striders silent indicators of ecosystem health, their presence signaling clean, functional surface chemistry, their absence hinting at unseen contamination. In calm conditions, reproduction adds another layer of risk. Mating often occurs directly on the water surface, where both individuals must maintain balance while engaged in prolonged contact. The slightest disturbance during this process can be fatal, yet the behavior persists because the water itself offers protection from terrestrial predators. Eggs are laid on floating vegetation or submerged substrates, placing the next generation immediately into this precarious environment. From the moment they emerge, juvenile striders must learn to interpret the surface, their smaller mass making them even more sensitive to disturbances, yet granting them agility that adults no longer possess. What defines the water strider is not merely its ability to stand on water, but its complete integration into a world defined by tension, vibration, and constant instability. It lives where solidity does not exist, where gravity is opposed not by ground, but by molecular cohesion. It hunts without sight, navigates without landmarks, and survives storms that would drown nearly any other insect within moments. This is not a marginal habitat. It is an extreme one, accessible only to organisms that have evolved to treat physics itself as a usable resource. In the end, the water strider occupies a realm that is lethal by default. The surface of water is a trap for most small creatures, a place where adhesion, surface collapse, and predation converge to erase life quickly and without warning. Yet the water strider thrives here, skating across a boundary that should not support it, reading chaos as information, and remaining upright when the world beneath its feet dissolves into violent motion. It survives where most insects would drown instantly, not by defying nature, but by understanding it more completely than almost anything else alive. For most of its existence, the cicada is not seen, not heard, and barely imagined. It exists underground, sealed away in darkness beneath forests, grasslands, and suburban soil, where time moves slowly and survival depends on restraint rather than action. While surface ecosystems burn, freeze, flood, and recover again, the cicada waits, anchored to plant roots, feeding on thin streams of xylem sap that carry little nutrition but offer steady consistency. This prolonged subterranean phase is not a developmental accident or evolutionary delay. It is a calculated strategy, one that treats time itself as armor. By stretching its life cycle across many years, the cicada avoids the volatility of surface life, where bad seasons can erase entire generations in a single stroke. Underground, the world is stable but not static. Soil temperatures change gradually, moisture seeps downward in pulses after rain, and plant roots thicken, die, and regrow around the hidden nymphs. Cicadas position themselves carefully along these routes, inserting specialized mouthparts into vascular tissue and drawing sustenance without killing the host plant. Their metabolism slows to match the limited energy supply, allowing growth without urgency. Predators are fewer here, and those that exist, such as burrowing mammals or predatory insects, are inconsistent threats rather than constant ones. This environment favors patience. A cicada that rushes development risks emerging during a year of drought, cold snaps, or ecological collapse, when reproduction would fail outright. Waiting underground allows entire cohorts to bypass these bad years entirely. This extended juvenile period also disrupts predator expectations. Surface predators operate on annual cycles, their populations rising and falling in response to predictable prey availability. Cicadas refuse to participate in this rhythm. By remaining absent for years at a time, they deny predators the ability to specialize on them. When they finally emerge, it is not as a trickle, but as a sudden biological flood. Millions rise simultaneously, overwhelming any predator response. Birds, reptiles, mammals, and even fish gorge themselves, yet barely dent the population. This is not resilience through strength or evasion, but through saturation. The cicada survives by being too abundant to consume. The trigger for emergence is not a calendar, but a convergence of environmental signals. Soil temperature plays a critical role, rising past a specific threshold that indicates sustained surface warmth rather than a temporary heat spike. This ensures that emergence does not coincide with false springs, when cold returns could kill newly emerged adults. Moisture also matters. Heavy rains soften the soil, allowing cicadas to tunnel upward without exhausting themselves or risking entrapment. When these conditions align, the ground opens. Nymphs climb upward through exit tunnels that may have been prepared weeks in advance, each one moving with urgency now absent for years. What follows is ecological shock. Forests that were quiet days before erupt with movement and sound. Cicadas crawl onto tree trunks, fence posts and buildings, shedding their nymphal skins in a synchronized molt that leaves the ground littered with brittle exoskeletons. Wings unfurl, harden, and begin to vibrate in the heat. For predators, this sudden abundance is a feast. For plants, it is a temporary stress. Branches may break under the weight of egg-laying females, leaves may be damaged, and nutrient flows briefly altered. Yet this disturbance is short-lived. The cicadas do not linger. Their adult lives are measured in weeks, not years. Heat shapes every moment of this above-ground phase. Cicadas are thermally sensitive animals, their muscles and nervous systems performing best within a narrow temperature range. Warm conditions allow rapid wing movement and sustained calling, while cooler temperatures slow activity and reduce mating success. This dependence ties their emergence tightly to climate patterns. During drought years, cicadas may still emerge, but survival becomes more precarious. Dehydration threatens adults that rely on plant fluids for moisture, and extreme heat can push body temperatures toward lethal limits. Some species respond by shifting activity to cooler parts of the day, calling intensely during mornings and evenings while remaining still during midday heat. Sound becomes the cicada's primary tool under these constraints. Calling is not casual communication. It is an urgent biological broadcast produced by specialized structures called tymbals that buckle inward and snap back with mechanical precision. Each contraction produces a sharp click, and rapid repetition turns clicks into sustained sound. The volume is extreme, not as a display of dominance, but as a solution to a narrow time window. Cicadas must locate mates quickly before dehydration, predation, or environmental change ends the opportunity entirely. Loud signals travel farther, cutting through wind, foliage, and competing calls, increasing the chance that receptive females will respond. This acoustic strategy carries risk. Sound attracts predators just as effectively as mates. Birds learn quickly to home in on the loudest callers, and parasitic flies exploit cicada songs to locate hosts for their larvae. Yet silence is not an option. A cicada that does not call will not reproduce. The balance favors volume because time is short. When emergence is synchronized, the danger of predation is diluted. A predator can only catch so many individuals, while thousands call at once. Noise becomes camouflage through excess, masking individual vulnerability within a wall of sound. The structure of the call itself is shaped by habitat. Forest-dwelling species produce lower frequency sounds that travel efficiently through dense vegetation, while open habitat species use higher frequencies suited to unobstructed air. Males adjust calling behavior based on temperature and humidity, accelerating or slowing rhythms to maintain optimal signal clarity. Females respond with subtle wing flicks or body movements, signals so quiet they require close proximity to detect. This forces males to continue calling loudly, scanning for any indication of reply before energy reserves are depleted. As quickly as it begins, the spectacle ends. Adults weaken, wings fray, and calling slows. Eggs hatch weeks later, and newly emerged nymphs drop from branches to the ground, disappearing once more into soil. The surface quiet returns, but the cycle continues beneath. The forest absorbs the remains, cicada bodies decomposing into nutrients that feed the very trees their offspring will one day depend upon. What looked like chaos resolves into contribution. The cicada's strategy reveals a deeper truth about survival in unstable environments. Rather than adapting to every bad season, it avoids them by delaying development, synchronizing emergence, and compressing reproduction into a brief, intense window. The cicada turns unpredictability into advantage. Heat and drought do not merely threaten it. They shape its timing, refine its signals, and limit its exposure. Sound, excess, and patience work together as a single system. In a world increasingly defined by climatic extremes, the cicada stands as a reminder that survival is not always about reacting faster, but about waiting longer and acting all at once. Its life is not a steady presence, but a countdown, ticking silently underground until conditions align. Then for a brief moment, the land vibrates with life, noise, and movement, before falling quiet again. The cicada does not endure disaster by resisting it. It times its life so precisely that disaster often passes before it ever arrives. In the forests of Madagascar, where weather can shift from suffocating humidity to sudden dryness and back again within days, survival favors creatures that can endure without moving far. The Madagascar hissing cockroach is not a runner, not a flyer, and not an insect that depends on evasion in open space. Its strength lies in refusal rather than reaction. While storms rip through leaf litter and heat drains moisture from exposed soil, this cockroach persists by reducing its interaction with the world to the smallest possible footprint. It survives not by conquering its environment, but by shrinking into it. Its body is built as a shield first and a machine second. The exoskeleton is thick, heavily reinforced, and darker than that of many related species, absorbing heat slowly and releasing it just as gradually. This armor does more than protect against crushing forces and predators. It limits water loss. Tiny pores that allow gas exchange are tightly regulated, opening only as needed to prevent dehydration in an environment where humidity fluctuates unpredictably. Where softer-bodied insects must remain active to regulate temperature and moisture, the cockroach can afford stillness. Remaining motionless is not a sign of vulnerability. It is a calculated conservation of resources. The forest floor is not a uniform habitat. It is a layered maze of decaying wood, leaf litter, soil cavities, and root systems, each with its own microclimate. The Madagascar cockroach exploits this complexity fully. It wedges itself into cracks beneath bark, into spaces between stones, or deep within rotting logs where temperature and humidity remain relatively stable. These microclimates act as natural bunkers. When surface conditions become lethal, the cockroach does not migrate or seek shelter in haste. It is already positioned where extremes are softened. Heat waves barely penetrate these spaces. Cold snaps arrive diluted. Even heavy rains that flood the upper leaf litter often leave deeper crevices dry enough to remain habitable. minimizing water loss, is central to this strategy. The cockroach's waxy cuticle forms a barrier that slows evaporation, while its behavior further reduces exposure. Activity peaks during periods when humidity is highest, often at night or after rainfall, allowing it to feed and move without excessive moisture loss. When conditions worsen, it retreats and waits. Metabolism slows, digestion becomes more efficient. The insect's digestive system is adapted to extract nutrients from low-quality food sources, such as decaying plant matter, fallen fruit, and organic debris. This diet is inconsistent and often nutrient-poor, but the cockroach compensates by wasting almost nothing. Energy is stored, reused, and rationed with precision. Predators still pose a constant threat in these confined spaces. Small mammals, reptiles, birds, and even other insects probe the same cracks and hollows. Escape routes are limited, and flight is not an option. When cornered, the Madagascar cockroach deploys a defense that relies on surprise rather than damage. It hisses. The sound is produced by forcefully expelling air through specialized spiracles, creating a sharp, sustained noise that echoes within enclosed spaces. In the darkness beneath logs and stones, this sudden burst of sound can be startling enough to disrupt an attack. Predators accustomed to silent prey hesitate, reassess, or withdraw, buying the cockroach precious moments to press deeper into crevices or brace itself against surfaces where it cannot easily be dislodged. This hiss serves multiple functions beyond defense. In confined environments where visual signals are limited, sound becomes a tool for establishing dominance and territory among individuals. Males hiss during competition, using volume and duration to signal strength without physical combat. This reduces injury risk in a species that cannot afford damage. A cracked exoskeleton or damaged limb in a low-resource environment could be fatal over time. Sound allows disputes to be settled efficiently, conserving energy and structural integrity. When environmental conditions deteriorate further during cyclones or prolonged droughts, the cockroach's strategy becomes even more apparent. Violent weather reshapes the forest floor, collapsing shelters, saturating soil, or stripping moisture from exposed layers. Many insects respond with frantic movement, attempting to outrun the change. The cockroach does the opposite. It presses into remaining stable spaces, reduces activity to near stillness, and waits for equilibrium to return. Its low oxygen demands and slow metabolism allow it to endure periods of scarcity that would starve more active species. Time becomes its ally. Reproduction follows the same philosophy. The Madagascar cockroach gives birth to live young, reducing the vulnerability of exposed eggs in an unpredictable environment. Offspring are produced when conditions are favorable, and juveniles immediately seek the same protected microhabitats as adults. Growth is slow but steady, matched to the availability of resources rather than an external schedule. There is no rush to mature if doing so would increase risk. Longevity itself becomes a survival adaptation, spreading reproductive effort across years instead of betting everything on a single season. The ecological role of this cockroach is easy to underestimate. By consuming decaying organic matter, it accelerates nutrient cycling within the forest, breaking down material that would otherwise accumulate and slow soil regeneration. Its waste returns processed nutrients to the ecosystem, supporting microbial communities and plant growth. In this way, its quiet persistence underpins systems far larger than itself. The cockroach is not a pest here. It is a stabilizer. What defines the Madagascar hissing cockroach is not invincibility, but endurance. Its armor does not make it untouchable. Its hiding places are not perfectly secure, but together, these traits create a system that favors survival over confrontation. When faced with heat, drought, or physical disturbance, it does not escalate. It withdraws, conserves, and waits. This strategy is not dramatic, but it is effective. In ecosystems shaped by volatility, resilience often belongs to those that demand the least. The Madagascar cockroach does not fight the world when conditions turn violent. It outlasts it, sheltered in the cracks of a forest that will eventually settle again. In deserts and arid scrublands where daylight scalds the ground and shade becomes a rare resource, survival is not measured by speed or strength, but by how little energy can be spent to remain alive. The black scorpion is an economist of extremes, an animal shaped not to conquer heat, but to negotiate with it. Its world is one where calories are scarce, Water is vanishingly rare, and mistakes are punished quickly. In this environment, excess movement is debt, exposure is risk, and restraint is profit. The scorpion's body reflects this philosophy immediately. Its dark exoskeleton is thick and armored, not built for flexibility but for durability and insulation. Beneath this shell, metabolic processes run at a pace that would seem sluggish in more forgiving habitats, yet here they are perfectly tuned. A scorpion consumes little oxygen, converts food into usable energy with remarkable efficiency, and can survive long periods without feeding. This low energy demand allows it to endure landscapes where prey is unpredictable and conditions swing violently between day and night. While many animals must constantly forage to offset high metabolic costs, the scorpion can wait, conserving resources until opportunity arrives. Daytime heat defines the scorpion's schedule by exclusion. When the sun climbs high and surface temperatures rise to levels that can cook unprotected tissue, the scorpion is absent. It retreats beneath rocks, into burrows, or into narrow soil fissures where temperature fluctuations are dampened. These microhabitats act as thermal vaults, keeping the scorpion's body within survivable limits while the world above becomes hostile. Remaining underground also minimizes water loss. The scorpion's cuticle slows evaporation, but behavior completes the defense. Stillness in shade preserves moisture far more effectively than movement in open air. Night transforms the landscape. Heat drains away, the ground cools, and the scorpion emerges into a world briefly permissive of life. This nocturnal activity pattern is not simply a preference but a necessity. Cooler temperatures reduce metabolic strain, allowing movement without catastrophic water loss. Many desert prey species follow similar schedules, creating a narrow overlap window where hunting becomes possible. The scorpion does not patrol this space actively. It selects a position and waits. Ambush hunting is the centerpiece of scorpion heat economics. Chasing prey across open ground would burn calories and expose the body to dehydration. Instead, the scorpion relies on patience and sensitivity. Specialized sensory hairs and slit-like receptors along its legs detect minute vibrations transmitted through sand and stone. Each footstep of a passing insect becomes readable information, revealing direction, size, and speed. Vision plays a minimal role. In darkness and cluttered terrain, vibration tells the truth faster. When prey comes within range, the attack is brief and decisive. Pincers seize first, immobilizing if possible without venom expenditure. Venom is costly to produce, both in energy and water content. It is not sprayed indiscriminately. The stinger is held in reserve, deployed only when necessary to subdue struggling prey or defend against genuine threats. This restraint is critical. A scorpion that exhausts its venom supply unnecessarily may survive the encounter, but fail later when faced with larger prey or predators. The venom itself is finely tuned, not to maximize pain but to achieve rapid control. In harsh environments, prolonged struggle benefits no one. Quick paralysis reduces energy loss and minimizes injury risk. Once prey is subdued, digestion begins externally, enzymes breaking down tissue before ingestion. This method allows the scorpion to extract nutrients efficiently from prey that may be consumed over extended periods, further spreading energy gain across time. Water conservation is embedded in every step of this process. Scorpions produce highly concentrated waste, minimizing fluid loss. They can derive much of their water needs from prey, reducing reliance on freestanding moisture that may not exist for months at a time. Even respiration is regulated to limit evaporation, with spiracles opening only when necessary. The result is an animal capable of enduring droughts that erase entire insect communities. Predators exist even here. Owls, rodents, reptiles, and larger arthropods all probe the night for movement. Against them, the scorpion relies on armor and posture as much as venom. Its rigid exoskeleton resists crushing bites, while its habit of pressing close to the ground reduces exposed surface area. When threatened, the scorpion raises its tail, not as a threat display, but as a calibrated deterrent. The stinger's presence communicates risk clearly. Many predators learn to avoid the silhouette altogether, recognizing that injury in such an environment can be fatal even if the scorpion is killed. Reproduction follows the same economic rules. Courtship is deliberate, minimizing exposure and energy expenditure. Young are born live and carried on the mother's back, protected during their most vulnerable stage. This investment increases survival rates in a landscape where abandoned offspring would perish quickly. Growth is slow, maturation delayed, until body mass and energy reserves can support independent survival. Longevity compensates for low reproductive frequency, spreading success across many seasons, rather than gambling on a single favorable year. What emerges from this system is not a creature defined by aggression, but by control. The black scorpion does not lash out constantly, does not waste venom, and does not challenge the environment directly. It calculates. It waits. It acts only when the return justifies the cost. In places where heat strips excess away and punishes inefficiency, this approach is not merely effective, it is essential. The stinger, often imagined as a symbol of constant danger, is in reality the final instrument in a carefully managed budget. Precision wins where endurance is tested daily. When the desert hardens and resources vanish, the scorpion does not fight the world around it. It negotiates with heat, pays as little as possible, and survives on balance rather than force. In temperate woodlands, weather does not arrive gently. Heavy rain drives soil into motion, wind snaps branches loose, and sudden temperature drops transform calm habitats into chaotic zones of falling debris and shifting ground. For the stag beetle, this turbulence is not an occasional inconvenience, but a defining feature of its world. Its survival strategy begins not with speed or stealth, but with structure. Thick armor, reinforced joints, and a body designed to absorb shock allow it to move through environments where softer insects would be crushed, torn, or simply overwhelmed by force. The stag beetle's exoskeleton is a living shield. Composed of layered chitin hardened through protein cross-linking, it forms a rigid outer shell, capable of deflecting impacts from falling bark, stones, and compacted soil. This armor is not evenly distributed. Critical areas such as the head, thorax, and wing covers are especially thick, protecting vital organs during collisions. The legs, though long and seemingly delicate, are anchored by joints that flex just enough to absorb shock without snapping. When storms rattle the forest floor, the beetle's body becomes a protective capsule, allowing it to endure physical punishment rather than evade it. This toughness matters because the stag beetle lives where weather funnels violence downward. Rotting logs collapse as they absorb water. Soil liquefies and then hardens again as rain passes. Leaf litter piles shift suddenly, burying smaller organisms beneath damp, compacted layers. For a beetle that spends much of its life close to the ground or inside decaying wood, these events are unavoidable. The exoskeleton acts as both barrier and brace, distributing force across the body rather than allowing it to concentrate at a single weak point. Even when trapped beneath debris, the beetle can survive long enough to exploit new escape routes created as the environment settles. Armor alone, however, is not enough. The stag beetle pairs physical resilience with behavioral restraint. Activity is not constant. Instead, it is carefully scheduled around environmental conditions that reduce risk. During heavy rain or high winds, the beetle withdraws into sheltered spaces, such as soil cavities, hollow logs, or deep bark fissures. These refuges buffer against both mechanical force and temperature swings. Remaining inactive during storms conserves energy and prevents unnecessary exposure to danger. When conditions stabilize, movement resumes. Humidity plays a central role in this timing. Stag beetles are highly sensitive to moisture levels, which influence both their hydration and the flexibility of their joints. Dry conditions increase the risk of desiccation and make movement energetically expensive, while moderate humidity softens substrates and reduces water loss. After rainfall, when the air is heavy with moisture and temperatures are moderate, the forest becomes briefly accessible. These windows are when the beetle feeds, searches for mates, and relocates between shelters. Activity compressed into favorable conditions minimizes risk while maximizing reward. Feeding itself reflects this calculated approach. Adult stag beetles consume tree sap and fermenting plant fluids, resources that become more available after storms damage bark and expose internal tissues. Rather than actively damaging trees, the beetle exploits these openings, feeding at night when evaporation is low and predators are less active. The timing aligns feeding opportunities with reduced environmental stress, further conserving energy and moisture. Larval life extends this strategy underground. Stag beetle larvae develop inside decaying wood, often for several years, insulated from surface chaos. These logs act as shock absorbers during storms, dispersing force and maintaining stable humidity. Inside this protected environment, larvae feed continuously on rotting wood, breaking down material that few organisms can digest efficiently. Growth is slow but steady, and development can pause when conditions outside are unfavorable. The larva does not rush toward adulthood. It waits until body size and resource availability align with a higher chance of survival above ground. When adulthood arrives, it brings new risks. The iconic mandibles of male stag beetles, often mistaken as weapons for predation, are primarily tools for competition. Battles occur not in open chaos, but on relatively stable surfaces such as tree trunks or logs, often during calm nights following humid days. Even these confrontations are governed by restraint. Rather than inflicting lethal damage, males grapple and attempt to dislodge rivals, conserving energy and avoiding injury that could compromise survival during future storms. Predators exploit weather too. Birds and mammals become more active after storms when prey is flushed from hiding. The stag beetle's response is not to flee blindly, but to freeze or press into surfaces where its dark, textured exoskeleton blends with wet wood and soil. Remaining motionless reduces detection, while armor provides a final layer of defense if contact occurs. Many predators learn quickly that attacking a heavily armored beetle yields low reward for high effort, especially when softer prey is abundant after rain. Temperature shifts add another layer of challenge. Sudden cold can immobilize insects that rely on warmth for muscle function. The stag beetle mitigates this through timing and shelter selection. By remaining within insulated microhabitats during cold snaps and emerging only when temperatures rise into a functional range, it avoids the paralysis that would leave it exposed. Its dark coloration also aids passive heat absorption during brief periods of sunlight, allowing it to warm more efficiently than lighter-colored insects. What becomes clear is that the stag beetle's apparent brute strength is only one part of its survival system. The armor allows it to survive impacts, but behavior determines how often those impacts occur. It does not challenge storms head-on or remain active regardless of conditions. Instead, it schedules its life around environmental rhythms, compressing risk into manageable windows and retreating when chaos dominates. This combination of physical durability and temporal discipline defines its success. In rough terrain shaped by falling debris, shifting substrates, and unpredictable weather, intelligence is not measured by problem-solving or speed. It is measured by knowing when not to act. The stag beetle may look like a brute, built to endure punishment, but it survives because it chooses its moments carefully. When the forest turns violent, it does not fight the storm. It waits, armored and patient, until the world settles enough to move again. In landscapes where rain can arrive sideways, wind can shred flight paths, and temperature swings can turn exposed surfaces hostile within hours, carpenter bees survive by reshaping their environment from the inside out. Their solution is not migration or mass sheltering, but construction. By carving nests directly into wood, these bees create climate-controlled refuges that buffer against rain, heat, cold, and predators alike. The nest is not merely a place to lay eggs, it is an engineered response to instability, a structure that converts an unpredictable world into a manageable interior. Wood offers a rare combination of properties. It insulates against temperature extremes, absorbs shock from wind-driven debris, and sheds water far more reliably than soil cavities or exposed plant stems. When a carpenter bee excavates a tunnel, it is not random destruction. The bee selects seasoned wood, often sun-warmed but structurally sound, avoiding material that is too soft or too damp. Inside, the tunnel remains remarkably stable. Temperature changes occur slowly. Humidity fluctuates within survivable limits. During heavy rain, when exposed insects are battered or drowned, the interior remains dry. When predators search bark and foliage, the entrance hole is small, defensible, and easily guarded. This architectural choice reshapes the bee's relationship with weather. Storms no longer dictate survival minute by minute. Instead, they become external events observed from within a protected chamber. Adults retreat during unfavorable conditions, conserving energy and reducing water loss. Developing larvae are shielded from both physical damage and thermal shock, allowing growth to proceed uninterrupted even when the outside world becomes temporarily uninhabitable. In this sense, carpenter bees do not endure weather so much as sidestep it. The nest itself is carefully structured. Tunnels extend inward before branching into brood cells, each separated by partitions made from chewed wood pulp. These walls regulate airflow and moisture, preventing mold growth and reducing the spread of parasites. Orientation matters as well. Nests are often angled slightly upward, discouraging water intrusion while allowing warm air to rise and circulate gently through the chamber. Even without conscious planning, the result is a passive climate control system shaped by evolutionary trial and error. Foraging behavior completes this system. Carpenter bees do not fly indiscriminately. They read the atmosphere with precision. Light levels signal temperature and predator activity. Wind speed determines flight efficiency and energy cost. Humidity affects nectar concentration and pollen availability. When storms approach, foraging intensity increases briefly, exploiting the last calm moments before conditions deteriorate. After rain, activity resumes quickly during breaks in wind, when flowers are freshly replenished and competition is reduced. This timing is not guesswork. Carpenter bees possess finely tuned sensory systems that detect subtle changes in air pressure, light polarization, and temperature gradients. These cues inform decisions about when to leave the nest and when to remain inside. Flying during strong wind wastes energy and increases the risk of injury. Flying during rain risks wing damage and loss of body heat. By restricting activity to narrow, favorable windows, the bee maximizes returns while minimizing exposure. The nest makes this patience possible. Without a secure interior, waiting would be fatal. Predators exploit weather too. Birds hunt more aggressively when insects are forced into the open by storms. Parasitic insects probe exposed nests after rainfall softens substrates. Carpenter bees counter this by limiting access points and maintaining vigilance at the entrance. Males, often mistaken for harmless loafers due to their lack of stingers, play a critical defensive role. They patrol nest openings, intercepting intruders and absorbing risk that would otherwise fall on reproductive females. This division of labor increases overall survival during volatile conditions. The most underestimated tool in this entire system is vibration. Carpenter bees are built around power. Their flight muscles are massive relative to body size, capable of contracting at high frequency without producing wing beats. This ability is often associated with buzzing flight, but its true importance lies elsewhere. Vibration is an engine that powers multiple survival tasks. During nest excavation, bees use controlled vibrations to chew through wood efficiently, breaking down fibers without exhausting themselves. This reduces construction time and limits exposure to predators while working. Vibration also enables buzz pollination, allowing carpenter bees to extract pollen from flowers that do not release it easily. This expands their foraging options, especially after storms when floral resources may be limited. By accessing plants that smaller or less powerful pollinators cannot exploit, carpenter bees maintain energy intake even when weather has reduced overall flower availability. The same muscular system stabilizes flight in turbulent air, allowing short, controlled movements during marginal conditions when weaker flyers would be grounded. Inside the nest, vibration serves yet another function. Subtle movements help regulate microclimate by shifting air and redistributing moisture. While not active ventilation in the human sense, these motions prevent stagnation and reduce fungal growth in humid periods. The nest remains habitable not because it is sealed completely, but because it breathes gently in response to activity. Larval development benefits directly from this engineered stability. Brood cells remain within a narrow temperature range, reducing developmental stress and increasing survival rates. In years with erratic weather, this advantage becomes decisive. While exposed nests fail and open habitats suffer population crashes, carpenter bee colonies persist, insulated from the worst extremes. Over time, this resilience shapes population structure, allowing bees to recolonize areas after disturbances more quickly than less protected species. Ecologically, carpenter bees influence far more than their own survival. Their nesting behavior creates secondary habitats. Abandoned tunnels are reused by other insects, spiders, and even small vertebrates. Pollination patterns shift based on their ability to forage during narrow weather windows, supporting plant species that rely on strong vibrational pollinators. In this way, their weather engineering extends outward, subtly stabilizing ecosystems that would otherwise be more vulnerable to climatic swings. What makes carpenter bees remarkable is not brute strength or aggression, but integration. Construction, timing, and vibration operate as a single system tuned to an unstable world. The nest absorbs the shock of weather. Behavior limits exposure. Muscular power converts vibration into versatility. Each trait reinforces the others, producing resilience without excess. When storms pass and light returns, carpenter bees emerge not as survivors scrambling to recover, but as residents stepping briefly outside a shelter that never truly failed them. Their world is not open sky alone. It is wood shaped into refuge, time shaped into opportunity, and vibration shaped into control. In a landscape ruled by weather, they do not merely adapt, they engineer. In tropical forests where rainfall arrives with sudden force and storms redraw the landscape without warning, leafcutter ants survive by treating instability as routine. Their world is not static ground, but a constantly shifting surface where trails collapse, soil liquefies, and familiar routes vanish overnight. For a solitary insect, such disruption would be catastrophic. For a leafcutter colony, it is simply another logistical problem to solve. What looks like chaos from above becomes, at ground level, a test of coordination, communication, and speed. The strength of the colony lies not in preventing damage, but in repairing it faster than the environment can exploit the weakness. A leafcutter ant trail is more than a path. It is infrastructure. These routes connect food sources to the nest with efficiency refined by millions of individual decisions. Pheromones laid down by foragers create chemical highways, invisible yet precise, guiding traffic across roots, stones, and fallen branches. Under dry conditions, these trails can persist for days, reinforced constantly by passing workers, but storms erase them in minutes. Rain dilutes chemical signals, washes away soil, and turns compacted paths into flowing channels. Branches fall, leaves pile up. What was once a smooth artery becomes impassable. The response is immediate. As soon as pheromone signals weaken or break, ants begin probing alternative routes. Individuals fan out, testing the terrain with antennae and legs, sampling moisture levels and surface stability. When one ant finds a viable detour, it marks the route with fresh pheromone, faint at first but rapidly reinforced as others follow. Traffic shifts organically, abandoning flooded paths and consolidating new ones within minutes. There is no central planner issuing commands. The colony reroutes itself through local feedback, adjusting flow where resistance increases and amplifying routes where movement remains efficient. Storms complicate this process by changing conditions constantly. A path that is usable one moment may collapse the next as water undercuts soil or debris shifts underfoot. Leafcutter ants compensate through redundancy. Multiple parallel trails often exist simultaneously, allowing traffic to redistribute instantly when one fails. Load sizes adjust as well. During unstable conditions, ants carry smaller leaf fragments, reducing the risk of slipping or being swept away. Movement slows slightly, but flow never stops entirely. The priority is continuity, not speed. All of this effort serves a deeper purpose than leaf collection alone. The true heart of the colony lies underground, where cultivated fungus provides the primary food source for larvae and adults alike. This fungal garden is exquisitely sensitive to environmental change. Excess moisture encourages mold. Dry conditions stall growth. Contamination can spread rapidly if not controlled. When storms threaten, the colony shifts focus inward. Entrance tunnels are narrowed or sealed temporarily with soil and leaf fragments, limiting water intrusion. Guards regulate traffic, preventing workers carrying contaminated material from entering sensitive chambers. Inside the nest, air circulation is actively managed. Ants adjust their movement patterns to direct airflow through the fungal chambers, redistributing humidity and heat. During heavy rain, when external moisture spikes, internal traffic slows to reduce humidity buildup. Waste removal routes are diverted away from food zones, preventing pathogens from spreading. Even brood placement changes. Larvae are relocated to chambers with more stable conditions, away from entrances where temperature and moisture fluctuate most. Predators exploit storms as well. Amphibians, birds, and other insects take advantage of disrupted trails and exposed workers. Leafcutter ants counter this through traffic control. When predation risk increases, workers cluster more densely along routes, reducing the vulnerability of isolated individuals. Soldiers position themselves at choke points, using mandibles to block access or fend off attackers. These defensive adjustments are temporary but precise, scaling up during peak danger and relaxing once conditions improve. What makes this system remarkable is its speed. The colony does not wait to assess the full extent of damage. It reacts continuously, updating routes and behaviors minute by minute. Pheromone concentrations rise and fall in real time, reflecting current conditions rather than past success. A trail that worked yesterday holds no authority today. The ants trust present feedback over memory, allowing rapid adaptation even when the environment remains unpredictable. Energy efficiency remains central throughout this process. Rebuilding trails costs time and effort, but failing to do so costs the colony its food supply. The ants balance these demands by prioritizing routes with the highest return. If a food source becomes too costly to reach due to repeated flooding, the colony abandons it temporarily, redirecting effort to closer or more stable plants. This flexibility prevents wasted labor and reduces exposure during prolonged storms. The fungus itself benefits from this logistical intelligence. By maintaining consistent leaf input despite external disruption, the colony stabilizes its internal food economy. When leaf delivery slows, fungal growth is regulated rather than allowed to collapse. Ants adjust feeding rates, consuming stored resources and slowing brood development until supply normalizes. This buffering capacity allows the colony to survive periods of extended rain or drought without catastrophic loss. As the storm passes, recovery is swift. Fresh trails replace washed-out ones, often in slightly altered configurations that reflect new terrain realities. Soil compacted by rain may harden into more durable paths. Fallen branches become bridges rather than obstacles. The colony incorporates these changes seamlessly, improving efficiency rather than merely restoring it. Each storm becomes a rehearsal for future disruption, refining the system through experience encoded not in memory, but in structure. What emerges from this constant adjustment is resilience, at a scale no individual could achieve. A single ant swept away by water is a loss barely registered. The system absorbs failure without collapsing. Traffic reroutes, roles shift. The city keeps functioning. Storms that would erase solitary insects from the landscape become temporary inconveniences to a colony that rebuilds faster than damage accumulates. The leafcutter ant does not resist weather through strength or shelter alone. It resists through coordination, flexibility, and relentless responsiveness. Trails are not fixed, rules are not rigid. Every ant acts as both worker and sensor, feeding information into a network that adapts continuously. One storm cannot beat a city that recalculates itself by the minute, turning disruption into another variable to manage rather than a force to fear. After heavy rain, the landscape that once offered concealment becomes exposed and unreliable. Leaf litter mats flatten, crevices fill with water, and vegetation bends or breaks under accumulated weight. For small insects that depend on hiding, these moments are especially dangerous. The shield bug lives through these periods not by fleeing or burrowing deeper, but by relying on a form of insurance that travels wherever it goes. Its defense is chemical, stored within its body, and released only when the balance of risk demands it. In environments reshaped by sudden weather, this invisible arsenal becomes more reliable than cover. The shield bug's body announces durability even before its chemistry is deployed. Its broad, flattened shape distributes force and makes it difficult to grasp. The hardened dorsal shield protects vital organs from impact and pressure when debris shifts or water drives material across the ground. But armor alone cannot deter predators that hunt by probing, biting, or swallowing. When hiding places are stripped away by rain, exposure increases and encounters become unavoidable. This is where chemical defense shifts from backup to primary strategy. Shield bugs produce defensive compounds in specialized glands, storing them until release is necessary. These chemicals are not generalized toxins meant to kill outright. Instead, they function as powerful deterrents, irritating mucous membranes, overwhelming sensory systems, and making the insect profoundly unpleasant to handle or consume. Predators that rely on taste and smell learn quickly. A single encounter is often enough to establish avoidance behavior that lasts for life. In this way, the shield bug invests energy not in repeated escapes, but in education. It teaches the ecosystem that it is a poor choice. Rain complicates this exchange. Heavy moisture alters how scents move through the air and across surfaces. Odors disperse differently in humid conditions, lingering longer, but traveling less predictably. For the shield bug, timing becomes critical. Releasing chemicals too early risks dilution, reducing effectiveness. Releasing them too late risks injury or death. The insect reads subtle cues in predator behavior and environmental conditions, adjusting its response accordingly. When contact is imminent and escape routes are limited, it discharges its chemical shield with precision. The warning phase often precedes release. Shield bugs adopt a posture that exposes their broad dorsal surface, making themselves visually conspicuous rather than attempting to hide. This behavior is not reckless. It serves as a signal, reinforcing learned associations in predators that have encountered similar insects before. Bright coloration or distinctive shape amplifies this effect, especially in environments where visual clarity improves after rain washes dust and debris from surfaces. The message is simple and efficient. Engagement will not be rewarding. Predators respond differently based on experience. Naive attackers may investigate, triggering chemical release and retreating rapidly once the deterrent takes effect. Experienced predators often avoid contact altogether, recognizing the silhouette and adjusting hunting strategies accordingly. This selective pressure shapes local predator communities, subtly influencing which species dominate after storms when prey distribution shifts. Weather also affects the shield bug's own physiology. Moist conditions reduce the risk of dehydration, allowing the insect to remain active longer without water loss. This increased activity window makes encounters more likely, increasing the importance of controlled chemical use. The shield bug does not waste its defense. Producing these compounds requires energy and resources that must be replenished through feeding. Overuse would leave the insect vulnerable later, especially if repeated storms extend periods of exposure. Chemical release itself is targeted. Rather than saturating the environment indiscriminately, the shield bug directs secretion toward the point of contact or threat. This focused deployment maximizes impact while conserving supply. In confined spaces, the scent becomes overwhelming, filling the immediate area and forcing predators to disengage. In open, rain-soaked environments, the same precision ensures the chemical remains potent long enough to serve its purpose before dispersing. Beyond individual survival, this strategy shapes population dynamics. Shield bugs can remain active in exposed environments where less defended insects retreat or perish. After storms, when competition for resources intensifies and predators adjust hunting behavior, shield bugs maintain access to food sources. Plants stressed by weather may produce softer tissues or altered sap flows, providing feeding opportunities that shield bugs can exploit with reduced competition. Reproduction benefits indirectly from this resilience. Adults that survive repeated exposure during volatile weather are more likely to reproduce successfully once conditions stabilize. Eggs laid in sheltered locations face fewer competitors and predators, improving offspring survival. Over time, this reinforces the value of chemical defense as a strategy not only for individual encounters, but for long-term persistence in unstable habitats. There is restraint here as well. Shield bugs do not broadcast their presence constantly. Silence and stillness remain preferred when conditions allow. Chemistry is reserved for moments when physical shelter fails or predators close in. This balance prevents unnecessary escalation and preserves the effectiveness of the defense when it matters most. In ecosystems shaped by sudden rain and shifting terrain, the shield bug occupies a niche defined by preparedness rather than speed. It does not outrun danger or disappear into cover. It confronts risk with a tool that remains reliable when the environment strips away other options. Predators learn. Encounters shorten. Survival rates rise. When chaos erases hiding places and the ground itself becomes unreliable, the shield bug does not panic. Its defense is already in place, carried within, waiting for the right moment. In a world where weather reshapes the rules without warning, chemistry becomes more than a weapon. It becomes a shield,